So our next talk is by the lead author and primary maintainer of ngspice. I know that there are a lot of interest in how to use Spice and how to effectively maintain it. In the past couple of versions, Spice integration has accelerated and improved in KiCad, and Holger Vogt will talk to us about all of the interesting aspects of how ngspice integration with KiCad is coming along. And if we're lucky, I think that there will be some advanced tips and tricks for effectively using ngspice in your designs at home. So please give a warm welcome to Holger Vogt.
Okay, many thanks to the KiCad team for having me invited to give a talk. A few words about myself. I'm a retired professor of University Duisburg-Essen. And you know, Essen is the city just right at Bochum's boundary, so it's not large travel I had to make to come here. That's great. Okay, I'm with ngspice for more than 20 years. Started as a hobby, and it is still a hobby. Well, I'm now coordinating a small team of developers. And I will talk about the specialty we have in that we use KiCad ngspice integrated into KiCad. I will talk a little bit about simulation, about ngspice as a tool, about the integration, and I will not go very deeply into simulation because, well, it can be a whole day, a whole semester, a whole year of talking. I will just coarsely give info about the simulation types available with the KiCad interface. I will hopefully working and do some live simulation here on this machine, give some more examples, and have a few words about information, further information. Yeah, why do we want to simulate circuits? There are some arguments available for emulating electronic hardware by software. And electronic is in brackets because you, of course, can simulate also mechanical or especially thermal things here. Well, you check the functionality of a circuit without the hardware being ready, so during development. You may easily test variants of the circuit. You just modify some parts, some pieces, and then you will get quick results. You save time and cost. So the way is you simulate, you verify, only then you build. Thus you reduce time and money consuming redesigns. I have a nice cursor, just don't know what it's doing here. It's not. Yeah, it's just, I don't know. You can check for the influence of parasitics. So you do a design, then you have a layout ready on board level or especially on IC level. It's just absolutely common. Then you check for all the parasitics, the resistances, the parasitic capacitances, and then you simulate again and you check if the circuit is still working. You can anticipate reliability, so you can do degradation simulation, or even radiation or sidewall attacks to be simulated before then they're occurring in reality. You can test entirely new concepts without too large an effort. And I think very important is also it's a vast learning experience. You look into the circuit. You can have a look at each of the nodes, what is happening there, what are the electrons and the voltages and the currents doing. And therefore we have ngspice. What is it? This is a circuit simulator. So It solves the nonlinear time-variant numerical equations, which are used to describe electronic circuits. And as a result of the simulation, we get the time-varying voltages and currents. ngspice is the open source successor of the venerable SPICE 3 from Berkeley, UC Berkeley. They started developing this and they made it open source very early. And so we are benefiting from them. And it's since more than 20 years now. Two applications are there around for ngspice. It's PCB design support, and that we support KiCad. We support also commercial tools like Eagle, and even Altium has grabbed a version of ngspice and developed it further, Fritzing, Depress, and others. Well, we need to have a comfortable user interface, and you will see, unfortunately, that ngspice itself doesn't offer that, so we rely on the third party. We rely on KiCad, for example. We have to be PSpice and LTSpice, the other famous simulators, compatible, at least concerning the models. So, yeah, that's what we do. On the other hand, there is IC design support. Integrated circuit development heavily relies on simulation. And there is a new, relatively new open source activities. There is open source PDKs, these process design kits available, where semiconductor companies offer the design data, and people want to simulate, and therefore we may use ngspice. So we have a requirement of having modern device models, these tiny 3 nanometer FinFET MOS transistors, and well, we have models for that. Okay, sometimes the circuits are very large. We have 200K transistors to simulate. We should be able to do that, and we should be compatible to another SPICE variant, HSPICE. Yeah, so standard ngspice is starting with the circuit. Well, it's not really starting with the circuit, but it's starting with a netlist. Yeah, this is a description, a SPICE netlist of this circuit. You include some model data files, you have some power supplies, you have these 2 transistors, simulation command, and some control commands how to run the simulation. And the result is the output. Well, this is an inverter, so green is the input, and of course inverted in red, the slight time delay is the output. Yeah, but netlist input is becoming quickly confusing because large circuits with 200K transistors have large megabyte netlists. You would not like to do that and check that and develop with that. You need schematic entry. And of course, this schematic entry with this graphical user interface gives also better documentation. You can group and visualize your input, and you can have a look at the output. Such a graphical user interface will lower the barrier for entering simulation. And well, all the other simulators have one, so we have to look for that. So I will not say that we ngspice choose KiCad for graphical user interface. It was the other way around. At some time, the KiCad developers found ngspice, and they started a very nice development on integrating this into the KiCad. And of course, now we are ngspice people benefiting from that a lot. There are other open source GUIs, especially for the IC development, but I'm talking today about the KiCad interface. And that's it, the KiCad interface. The integration of ngspice into KiCad, especially is into Eeschema. Eeschema allows schematic entry. Eeschema generates the SPICE netlist, and Eeschema offers the graphical presentation of the results. So it sends circuit netlist to ngspice simulator, model parameters are sent, simulation commands are sent to the simulator, and the simulator sends back the simulation results. The simulator itself is in a form of a shared library. So this is a well, a little bit special version of ngspice in that this has no outside interface, or typically nearly no interface. All the interfacing is handled by Eeschema. But this allows a very close, very direct integration. Yeah, and this is how it looks like. You have the Eeschema window, oscillator circuit here, and there's a special simulator window, and this simulator window shows the simulation results, offers a little bit more. You can do something, you can handle these results a little bit to get special interfacing. For example, this is the oscillator, and this is a fast Fourier transform of the oscillating signal, and you can have a look if the frequency is right or not. Well, I will do a small example, a simple example, because, of course, we are starting with the simulation. So this is a simple circuit. Well, people doing analog design know what it is. It's a bipolar transistor, biased accordingly to be an audio amplifier. You have the input about over a capacitor, the appropriate DC biasing, and the output here. And there is one specific to the simulation itself, and that the simulator, of course, needs to know what kind of voltages do you put on to your circuit. And therefore we have, there's a special library part, the simulation spice library, which offers these devices as a DC voltage source or a AC voltage source, and these are coupled, okay, here via the global tags into the circuit. What kind of simulation types are then available? The first is the operating point simulation. What do? We do a little bit with a circuit that ngspice is doing this. It opens all capacitors. It shorts all inductors, and then it puts all the voltages onto the circuit, the voltages we have here. And then it does a calculation. It calculates all node voltages and branch currents. And these all are visualized here on the Eeschema simulator window. Come to that back a little bit later. Well, operating point. So it's a DC thing. We are mostly interested in the time varying simulation. Yeah. So what do we do then? Use the same, whatever circuit. We have the operating point calculated as a starting point. Then we are interested in the time-dependent behavior of the circuit. So these voltage sources we have had on our circuit are now sending their time-dependent voltages into the circuit. Well, the DC voltage is hopefully not time-dependent, but the AC, of course, is. And then we do a simulation that all node voltages and branch currents are calculated time step per time step. So the simulator makes tiny time steps and calculates the voltages and currents. And for example, we have here in our amplifier the input, the output, and the input is in red, the voltage in, the sinusoidal 1 kilohertz, and the output is this sinusoidal in blue. It's inverted because, well, simple amplifiers are inverting, and it's amplified by a factor of 3, roughly. Okay, so this is the 1 kilohertz thing, but we of course are also interested in how is the circuit behaving with varying frequencies, because of course not only the 1 kilohertz, we have, well, maybe the audio frequency starting at 10 hertz and going up to, for me it's kilohertz, but for you it's perhaps tens of kilohertz. Yeah, and there we have another simulation type. So we had the operating point, we had the transient, so versus time, and now we have the simulation versus frequency. And this is called small signal AC simulation. We have the operating point calculated. This is very important because depending on what DC voltages you put onto your circuit, of course, the operating point may change and the circuit behavior will change. So you put a special DC variant onto the circuit, hopefully the optimum thing, and we calculate the operating point. And then the simulator is doing something that we have a lot of nonlinear elements in our circuit. All transistors are nonlinear, diodes, well, you know, all these devices. We have, of course, also linear ones, which is capacitors, inductors, resistors. All nonlinear elements are linearized around this operating point. Yeah, so we look at this DC point and make a little up and down and see what the slope of the curve then is, and this is the linearization. And the resistances of all these node-to-node nonlinear devices are determined. And then, of course, we put frequency on, and then we calculate the resistances of the inductors and capacitors. And then we have a matrix of linear elements. And then we do a complete simulation, frequency per frequency, of this linear network. And the output is then relatively calculated relatively to the input, of course, because we have a linear network. And this is what the output is. This is a frequency starting at 1 hertz, going up to 10 megahertz for this device. And you see there is some high pass behavior because of the emitter feedback circuit we have chosen for this tiny transistor amplifier. Then there is a flat top, flat from 100 kilohertz to maybe a few hundred, from 100 hertz to a few hundred kilohertz. And then it goes down because this is the fate of all amplifiers at high frequency. They degrade again. And the plot here shows the gain, and the plot also shows the phase. So we have a phase shift of our signal, of course. And that's what you see here. And these operating point, transient simulation, and AC simulation are the most important simulation types we have. There are several others, but these prevail. So let's check if I can do some live simulation. Well, this is installed here on this machine is KiCad 8.0.5, ngspice 42. And this is not a very fast, it's an elderly notebook, two cores only. But okay, for these tiny simulations, we are quickly, I just open the Eeschema window, and here we are. Just enlarge this a little bit. Okay. Yeah, again, you see our amplifier. And now we want to do these simulations. We have a look, and this is the inspect simulator. Opens up the simulator window. Well, okay, I have to confess, I have prepared the 3 simulations here already. Let's do the operating point simulation. So this is the blank circuit, and I do the operating point simulation now. And you see the data here have filled up, and you can have a look. You see that there is about 2.6 milliamp total power drain. There is about 2 milliamp floating into the collector of the transistor. And you see the DC voltages in brown and the currents in red. And then you can quickly, if you know a little bit about circuit design, you look at this and you quickly say, okay, basically seems to be okay. Okay, so this is the operating point simulation. The next analysis I want to do is a transient simulation. I open this transient window. I just have a look at what do we do here. This window I have put in this time step, 10 microns, and the final time, so the total simulation time I want to do is 10 milli. For 1 kilohertz signal, this seems to be fine. I can check if I want to save currents, power, and so on. This looks nice. And then I just start simulation, and that's it. So this is, even if this computer is not the hottest machine, you see this is very fast for these simple, tiny circuits. Of course, you could have a large circuit, then it would take a little bit longer, but that's it. So we have immediately, and we can see here, we can have a look at other signals. I don't know if they're of interest. Okay, this is, what did I switch on here? I don't know. Yeah, the VDD, of course, is 12 volt. Not that interesting because it's constant. Yeah, so this is the transient simulation. Next simulation I can do is the AC simulation. Again, I have a look at the data. I do a logarithmic scale of the frequency. And I've chosen 10 points per decade, 10 frequency points per decade. Starting frequency is 1 hertz, and the final frequency is 10 megahertz. Okay, I don't need the currents and power dissipation, just save the voltages. And yeah, that's it. The AC simulation typically is very fast. And here I've chosen the output gain and output phase to be plotted. Yeah, so this is simulation, that's it. That's all. Okay, we don't save anything. Yeah, there is some other examples. Let's do this one here. Just open Eeschema again with this circuit. This is a simulation, a basic simulation of a digital power amplifier. If we look here, the power supply is plus minus 103 volt. So this is a lot. We have switches here, the transistors. We have an output filter here, and we have some. We have some input circuit. This is not a live IC. You could have these ICs, but this is a homemade basic model. We can have a look at this. If I go into the simulation model, and if I go here into pin assignments, I can even have a look at what is inside of my model. So it's a sub-circuit model, audio driver model. I have put a PWM into this. I have some drivers. I have some buffers. I have inverting and non-inverting. All this put together into a sub-circuit. I have made a symbol, homemade symbol, very simple thing, just a rectangle with some pins, and put this circuit in here. And this is driving my transistors, and the output out is going to a load, 2 ohms of loudspeaker. Okay, and let's check what we can do here. Yeah, just do the transient simulation. And you see now the simulation is a little bit slower. You can follow it live. Again, 1 kilohertz signal. The interesting thing for this circuit is I have also saved the power in the R15 in the loudspeaker. and did an RMS calculation, which is automatically possible by right-clicking onto this signal here. And you see this amplifier is delivering 2.6 kilowatt. These Class D amplifiers, digital amplifiers, are offering a relatively simple and even says cheap method of making a lot of audio noise. And the simulation of this has some advantages. Imagine that you build such a thing and then something goes wrong. What will happen? It will blow up. The simulator may blow up, but only mathematically, never real. Yeah, and so you just see if something is wrong from the beginning. You can have a look at this simulation, and then you figure out what to improve. We have the input signal here. We have the output in green, and we have this power signal with double frequency, of course, because plus and minus always give the power output. And the RMS is a lot. Yeah. And then you can do the development, I will not show this here, or refinement of this circuit, putting in real devices, or you can use this just as study for the output filters, or what you could study is feedback. How can I use these signals to feed back into my amplifier, or whatever. And this can always be done relatively quickly, quasi live. You can also do some totally different simulation. Well, the most famous IC, I think, is the 555 oscillator, which in fact is an integrated circuit. And I've just drawn here the interior of this integrated circuit, MOS transistors, PMOS and NMOS, so it's a CMOS device. And they have a special width and length, which is not common for the standard off-the-shelf transistors, but for the ICs, of course. And this is what I want to build here or to show here. This is our device, and this is a circuit. And okay, you find the circuit just here. This is the circuit to run this oscillator. Okay, inspect simulator, transient simulation. We're looking at 1 micron and 2 milliseconds total simulation time. And then we start simulating. Well, and here we are. We see the oscillators, they need sometimes some time because they like to start up. And then there's a 50% duty cycle simulation. Yeah, fine here. Yeah, so much about some live simulations. We are, of course, continuously working on ngspice. We have not all of these new things are already integrated into KiCad, or sometimes we have to check if this is useful to do this. For example, we are just now working on RF simulation. We're supporting S parameters, but we will add harmonic balance simulation type in ngspice. We have more than 60 analog and digital ngspice components, and one could think of, does it make sense to make a library for these devices? We support Verilog A compact device models for these modern transistors, but also we support Verilog digital circuit blocks right now. And we have to check if it is useful to integrate this into KiCad somehow. Yeah. So Verilog allows to make digital circuits. We translate them with Verilator or Icarus, and then can attach them to ngspice, and then do a mixed signal simulation. Some analog part, maybe sensor part or whatever, and some digital part. We also can read C-coded circuit blocks. Something which is again interesting, and I've used this much and even also made a tutorial out of that, is electrothermal simulation. There was a question in the morning on the heat generated by the CPUs in this tiny notebook. Well, all electronic devices generate heat. and the heat is flowing, and the heat makes temperature differences. And you can translate this into electronics, temperature differences, voltage difference. Here, heat flow is something like current and so on. And so you can make electronic lumped element circuits for your heat system and simulate this together with the electronic system. Another example is, for example, this amplifier for the audiophile people. Just the results, input, output, power. We can do this mixed signal simulation, a simple mixed signal simulation using these venerable 74 devices, CMOS or whatever. Shown here is a rotary encoder. It has some analog part, which is here, because the analog part makes some delay and so serves for a clock with a specific delay determined width. And well, the output here is not plotted with the KiCad. Digital is not the main domain for now. So we use in addition GTK wave just integrated by a script into the simulation. Or we can use one of these ngspice models, up-down counter with a state machine, another simply generated symbol, input pulses, one is for up and one is for down, the other is the clock, up, down, and clock, and the output is 3 digital devices or 3 digital signals, and these are now plotted here, just added, and it counts up, and then it switches to count down. Simulated, and this simulation time here, because the digital simulation in ngspice is very fast, simulation time here is a mere 37 milliseconds. If you want to start simulating, I could recommend you my YouTube channel. I made 8 relatively simple videos. Simulation basics, for example, how to place resistors onto the Eeschema canvas, a voltage source, and do an operating point simulation of a voltage divider. Then how to make an amplification with an op-amp, generic op-amp, which is integrated into KiCad or Eeschema. You even don't need to look for a model, you have it already there. But if you want to do a commercial operational amplifier, you need to grab a model from outside. KiCad, ngspice, we don't deliver models without distribution because of a lot of issues, legal issues, and whatever. But of course, you can just go to the TI website, download the SPICE model of this device, and do simulation. We have this bipolar amplifier optimized. We have oscillators. We have mixed signal simulation. Just have a look and learn how to use ngspice. If you go looking for more advanced examples, well, there are in the forum, in the KiCad forum, I have 2. It's not issues. It's 2 threads with examples. For example, a DC-DC converter using a specific IC, another DC-DC converter using another specific IC, or a DC-DC converter made of basic building blocks just to learn how a thing is working. You have the switch, you have a pulse width modulator circuit, and you have the arrow amplifier, and you can just play around with these to learn. If you're as old as I am, you may be interested in simulating tubes. You can do that. Another oscillator or a specific audio amplifier, class A, drawing a mere 200 watt to deliver 20 watt of audio signal. But there are people saying this is the real thing. Okay, so what's next in ngspice? Some ideas, some plans, some actual projects. We improve the RF capability by adding harmonic balance. We support reliability and degradation simulation. And in fact, this is the first time ever since 20 years that we have got some funding for doing this from the National Research Ministry, being part of a large open source development project. People asking for a simulation of transient noise, okay, a special thing. This is something which has to be done continuously, I think. You improve the usability of the interface. There is well, some issues, some wish list issues open, and if you have the idea to have more, just place them there, and people will hopefully find some time to work on this. In ngspice, we improve the error messages. Well, the original SPICE was, yeah, you sit on the computer, you type a command, and if you do something wrong, you get immediately the feedback. Now, in the time where you run lots of scripts and lengthy simulations, this is not that useful always. Yeah? So we improve error messages, for example, telling the customer where to find the error. In which file, input file, or whatever. We look at better support of analog building blocks. We might, yeah, if somebody is interested, this is, yeah, probably a library issue, yeah, to add these building blocks to a specific library in Eeschema. What people are asking, and I'm just considering to do this, is a step command to make loops, yeah, simulate varying parameters, not only in one dimension, but in 2 or 3 dimensions. Oh, okay. This will be not in the next ngspice release, but in the one following, hopefully. Yeah. There is some links to info and support. We have ngspice discussion forums. We have the ngspice manual. It's meanwhile 800 pages. So very important also is the KiCad info forum, where I'm also active. I'm only answering questions concerning simulation, nothing else. We have the KiCad manual with this simulator. I have made some tutorials for beginners, control language, KiCad ngspice interface, or electrothermal. We have these introductory videos. There are model parameters collected by people, and I've put this together. And we have the simulation examples. Yeah, that's what I want to tell you about the simulator right now. And thanking you for your interest. And if there are questions, please.
Thanks. Hi. I'm working with circuits of a very quite high frequencies, and I was wondering, when it comes to ngspice implementations and those calculations on non-linear equations down there, is there any limit when it comes to frequencies at which or over which we should be concerned about numerical errors inside the simulation engine? Right now we are working with circuits below 1 gigahertz, but we are aiming to step forward to up to 24 gigahertz. So it's quite an advanced, and we are wondering how reliable we can be with the results.
Yeah.
Thanks.
There is no basic limit because mathematics is the same. It's very strongly depending on the device models, and it's depending on the interfaces between the devices. If you talk about integrated circuits, for example, we are now working together with the IHP institution in Frankfurt-Oder, and they develop transistors running up to 450 or 500 gigahertz, bipolar transistors. And we have the models for this, and it can be done. If we talk about boards, I think the critical issue, and there is some work going on, but it's not yet finished, is on extracting the parasitics. How much capacitance do you have? When you send a signal from the output port to some other device, what will happen? Will it be reflected? This modeling is tricky. Electromagnetic solvers are to be involved. There is some things going on, but this is not user ready right now. So I would say the ngspice simulator itself, if you have the correct device models, no limit.
Hi, thanks for the presentation. Can you say a few words about compatibility with models? I think I saw in your presentation that it was fully compatible with LT-SPICE model of devices, of real devices.
It is compatible. It is not fully compatible. Because the problem here is LT-SPICE and the others are not open source. So how to make things fully compatible is not possible. Again, the simulator kernel is the same for most of the SPICEs around in the world. The access to models is the other thing. We try to be compatible to models written for PSpice, for example. And most of these operation amplifier models and ICs offered by Texas Instruments, for example, they have a PSpice simulation model. And we have to be compatible to that. Yeah. Typically, I have to confess, sometimes people say, oh, I do a simulation and the output is nonsense and the simulator is bad. What do? I put this into LT-SPICE. And the output is the same nonsense. So probably it's not the simulator, but it's the input. Yeah. So compatibility, yes, but limited. And there is another issue which is severe because we are open source, and there is a movement by these semiconductor device makers to make encrypted device models. We cannot use them because, well, legally it's not allowed to break encryption, and we don't know how to break encryption, and I cannot care about that. So this is a limitation on compatibility.
Hi, thanks for the talk. But is it possible when I try to start a design in Eeschema and I want to go to a board, is it possible that I can use the same schematic, or do I need a completely separate schematic where I only need to simulate the parts I want to analyze, or can I analyze the whole schematic?
Yeah, this is a little bit, this is a discussion going on in the KiCad info forum, for example. Several threads are about exactly that. What is the best way to simulate? There are people saying, okay, if it's a simple circuit, you may use the same layout. But of course, you have to place some additional devices like voltage sources onto the schema for simulation, but you can exclude them from board. Yeah. So, same as you could say, okay, I need some additional devices to ease simulation. I would not like to put them on board. Or I have something on board which connectors, for example, which I would not like to simulate. Then you can exclude them from simulation. This can be done. So other people say, okay, it's better to make a copy. And it's often, if you are new to simulation, it's not a good idea to start with simulating the whole thing. This will typically never work. You have to simulate blocks. And then, of course, one has to consider how to do that. And I think the best is then you cut out these blocks, copy them, and put them into additional small simulation project. You could think about doing this a little bit more integrated. Well, why not make a rectangle? But and you cut some wires, and you have to cut these wires somehow. And you have to put SPICE voltages on. And to automate this, I don't know. Could be done, perhaps. But for now, I would recommend small circuits, simulate them directly. Larger circuits, put them into individual blocks and copy them and then simulate.
Thank you for your presentation. What's about parasitics? We are in a PCB design tool. Can you simulate parasitics from the PCBs?
I have to think how to interpret this question. I can simulate them, but I need to have the data. Yeah, what are parasitics? Parasitics could be series resistance and capacitances to ground and to other wires. Or parasitics could be, if I really on high frequency, to say, okay, a sort of transmission line behavior. I can simulate, ngspice can simulate these, but there is currently no straightforward way to extract the parasitics. This is something which would be interesting to work on. The IC design people, they have this. They need this, absolutely. And this is a software which costs yearly $500 or more, license costs. A stripped down version, because on PC board everything is larger, could be done, could be developed. There is some work going on with electromagnetic solvers, but so these field solvers, but these are typically research softwares, and this is difficult for don't be despectively, but for average electronic designer to use an EM solver. I think this is nearly a no-go. Yeah, so we have to figure that out. I think this is still missing. There is something integrated already into the Eeschema. This is so-called IBIS, signal integrity checks. Yeah, that the vendors, they offer IBIS models. These are interface models, not models for the whole MCU, but for the output or the input. Then you can check if you send a signal, will it be the right signal at the receiver? But still, what is missing is what is in between. How do we calculate this?
What we have as problem is we have a trace. We have 200 millimeter trace is half millimeter in wide. And then very fine if I can easily simulate the parasitics of my trace and of the ground plane, how it works together. And we are in the schematics, and then maybe there was possibility to add a tool to extract the parasitics from my PCB I do, and then can I simulate that?
Yeah, if you have this tool for extraction and you get the data, then you can simulate it.
Just a mini question. I saw on your 5x5 timer you had like the width and the length, so you had like a common substrate process. When I want to do something like that, how would I do that, or would you say don't try it in KiCad and use one of the other options?
Yeah, this is IC simulation, integrated circuit simulation. You can do that. This is the 555 is a very simple, tiny, old design. It's okay. Also did some operational amplifier, or did this venerable generator of rectangle and square, the 8038 thing. You can put these transistors together and simulate this. The simulation is absolutely not the limit, but the question is, how much sense does it make to do this in KiCad? Putting 10 or 20 or 50 transistors onto the Eeschema canvas manually, yeah, you can do it. You can interconnect them, and then you can simulate it. No technical problem. I think it's a little bit up to you. If you like this interface, which is just for testing. KiCad is not made for IC development. So, yeah. If you like it, you can do it.
Hello. You mentioned that you can simulate degradation effects. How is it made? I think degradation is a verification of parameters of the models, and I assume that normal models would not provide that in an easy way. So how is it made?
Yeah, I said we are working on this. We have just started working on this. So we cannot right now, but we will do 1 year or 2 years from now, we will have that. Yeah, the first idea, of course, is not to intrude into the models, because these models are so complex that this would be risky. Now we have a look at the model parameters. What is degradation? Degradation, for example, when you do degradation radiation, ESA and co, then the mobility of the transistors go down and the threshold voltage shifts. This can be expressed in a parameter shift. So you have to calculate the parameter shift and then just do normal simulation. And there are models available, and people are working on new models to calculate this parameter shift, either just over time, running a circuit for 10 years under specific conditions, what will be the parameter shift, and then do resimulation. I think this is possible.
Thank you very much for the talk. As it's an open source project, I'm just sort of interested, are there particular areas where where the project needs support in particular?
Yes. I would be happy about the interface. The interface which I've shown is very nice. It's a good starting point, but it's still somewhat limited. Simple things like if you have a plot of the output, just to say I want to have logarithmic or linear. Currently, there is no button or no tick box to check that. This could be done. Or if you do simulation and you have several signals you are interested in, you would like to have them on top of each other. You can do it a little bit manually by adding some voltage and just so having this on a single display, but could be done better. So usability actions, improving the interface could be make things a lot better. But this would require to delve a little bit into the Eeschema coding. Concerning ngspice, if there is something, this is my task, or the task of our development group. We do that, and we have benefited a lot from these bug reports. I think when we started, there were a lot of bug reports. ngspice crashes the whole thing. I think in the last year or so, we don't hear this anymore because we have worked on these bugs. Yeah. What else could I imagine? I think a lot of things. But the direct work on the interface, because, well, developers do, but the time is limited. And if you say, okay, I know C++ and I have some time and I will full-time interface simulator developer, you're my person.
Yeah. Thank you again for the great talk. Quick question: you said in the outlook that you're focusing more on the RF high frequency simulations, basically. S parameter simulations, are they available? And if so, or if they're about to be available at some point, do we have like models for generic lines or stuff like that?
What we can do right now is generating S parameters of whatever circuit. So we have to do two ports or even more than two, and then just generate the S parameters out of that. What we also can do is doing S parameter simulation on small signal. So sort of AC simulation with S parameters at the building block. Then you get lumped element circuit out of your S parameters and can simulate that. What we cannot do right now is large signal S parameters or large signal RF. And this is what harmonic balance will offer. But this takes some time, and it will take another, ask me in 2 years.
Okay, thank you very much, Holger.